for inviting me. Hello, everyone. So yes, my name is Nicolas Larrosa. I don't need. Can you hear me from the back? Yeah. So my name is Nicolas Larrosa. I am associate professor in Bristol. So what I'm presenting today is a method that we have been working recently to try to link design and assessment. I come from a fraction mechanics background, and very recently, due to projects, I started to engage a little bit more with design codes, and kind of strikes me the fact that there's no strong link between design and assessment, and you can design something which is according to code and standards, but then from day one it might not be fit for purpose. If there's a crack, if there's a flaw. So damage tolerance design is something that I have been very much interested during the last year and a half probably, because I started working with hydrogen, and I started engaging with the hydrogen industry, pressure vessels, pipelines, TSOs, trying to repurpose infrastructure, and that's why I started working in developing this methodology to try to link design and assessment. So I want to thank also some of my collaborators. This is a work that I started myself, but I needed a lot of people to support me and to help me, especially with the calculations and to trying to give me some feedback on how the method works. So, all right, it's frozen for some reason. Yeah, it's frozen. Oh no, yeah, it's frozen. I am frozen. Yeah, it's not.
Is it okay?
Is it moving? Oh yeah, it's moving now. Okay, so this is kind of the outline of my presentation. I'll try to bring the concept and motivate it first. So in essence, if you go to design codes, basically we have a cap on the maximum stress, and in pressure vessels, typically what they do, we have a safety factor or a design factor, which is applied to basically cap the maximum stress we can have in our pressure vessels. So if it's a pipeline tip or a storage tank cylindrical, that would be the hoop stress, the circumferential stress, right? So that's what we get in the codes. But unfortunately, codes, as I said, they have some limitations. They are based on stresses. There's no clear interaction between mechanisms, corrosion, and brittlement. How do you actually follow the evolution of the material properties? Interaction of, as I said, multi-axial state stress. Some of them, or most of them, doesn't really include defects. And when they include defects, they take you to an FAD assessment, which requires some expertise, requires some understanding, fracture mechanics expertise, and also residual stresses are not typically included in design codes. So you might wonder, probably bless you. So probably we can do better. If you use the FAD for a design, both parameters have always struck me the fact that both parameters are load dependent, material dependent, and flow size dependent. So it's not, and the shape of the FAD is quite cumbersome, right? The nice thing about an FAD is that you can use an elastic analysis to do an elastoplastic analysis. But if you have a point somewhere here, and then you have a change of material properties, and you want to do some sort of a parametric analysis to see where you are, and given the fact that the point will move in different ways, and the shape of the curve is somewhat, cumbersome, it's not very intuitive. It's not really straightforward to do rapid assessment. And changes in parameters means that you have to change LR and KR. Unfortunately, I cannot explain what this is if you don't have a background on this. But if you come to my next presentation at 4, I will be detailing a bit more about this. But in essence, oh, the other way around. In essence, what I'm trying to say here is that, the FAD is not very practical for design workflows, and I think we can do better. So, my God, this is not working very well. So I think we can do better, and I think we need a more intuitive and straightforward way of designing, and in one which we can actually have safety margins or safety targets embedded in the methodology. So the way we approach this, if you think about how the driving force of a fracture is considered in a normal FAD, this is kind of a very simple but kind of complete description where you have the primary loading, you have the residual stresses, and you have a factor which actually accounts for the reduction or the interaction of the load with the residual stresses. A very high loading, typically residual stresses, they wash out, they reduced due to plasticity accommodation, and you have also the material resistance to fraction. In very general terms, Kmat. If we rewrite this by normalizing the primary load and the residual stresses by the yield strength, we can have a normalized parameter for the primary loading and the normalized parameter for the residual stresses. Here, an assumption is that we are going to use residual stresses as a membrane stress. Okay? That's an assumption. You can criticize it, but this is the first step. So we will write KR like this, right? No big changes. Just we have two non-dimensional parameters which describe primary and secondary loads. At failure, we can say that KR is basically the value of the critical condition is FLR in an FAD framework. So we can we change KR and we can rework this equation to get primary and secondary stresses as a function of configuration and critical conditions. As I said, more details about this in our coming paper. So I define this term as K hat. It's a normalized configuration of toughness. This is the primary loading, and this is the residual stress or secondary stresses effect. I say residual stresses actually are secondary stresses. It could be thermal stresses as well. Yeah. So, in essence, we have a critical primary load given as a function of a configuration and material properties under the effect of secondary stresses in this equation. So what we did, we performed a large number of FAD assessments to get the critical value of the primary loading. Actually, we did 588,000 FAD analysis using FFS signal, which replicates API 579. You can see here that we did different normalized diameters, different normalized crack depth from 0.1 to 0.7, different crack aspect ratios, 35 different values of fracture toughness from 10 megapascal square root meters to 350, 5 different yield strengths, and different levels of residual stresses from 0 to 100% of a yield strength. So if you plot this, there's nothing really new. It's just a line because basically we are plotting the normalized pressure over this term, right? So it's a straight line, but it's quite reassuring. What we want to do here is actually have the value of the normalized global stresses as a function of these parameters and try to remove this from the equation, right? Because this already has the load. So let's try to remove that. What we did, in simple terms, we just removed this term from the equation. And now we have, for the 5 different levels of residual stresses that we tested, we have the primary stress as a function of the normalized toughness for the given values of residual stresses. So this framework, if you believe in it, will allow you to evaluate, let's say, the pressure that a specific configuration and material could be able to withstand for certain material properties and dimensions. Yeah? When I say dimensions, I mean crack shapes, diameter of the cylinder, and so on and so forth. So as you can see, the results collapse quite well, right? Results collapse quite well when you write it in this way. So it's quite encouraging to see, although there's some spread in the data, it's quite encouraging to see that. So this is a framework. In essence, you've got a loading parameter and a material and configuration parameter, which are independent, right? You don't have in both places loading and in both places crack size and in both places materials, in both axes, I mean. You just have loading, primary loading and configurational aspects, which makes it very simple, very nice for design purposes. You can get here with your material properties and your configuration and see what are the limiting states for different residual stress levels. Yeah, I hope the concept is clear. Some other interesting aspects here. You no longer really need the reference stress. We don't longer need the reference stress. For pressure vessels, I forgot to say that we model axial, internal and external, and circumferential external and external cracks. Yeah. So for pressure vessels, the reference stress is, and the range of cases that we analyze it from, about 0.1 to 0.7, and the aspect ratios of about 0.25 to 1. The reference stress is almost the global stress, the nominal stress. Yeah. So there's no huge difference. Right. Some application to hydrogen, because I have not talked about hydrogen yet. So if we think about this lambda value, and you go to the ASME V31 code, which by the way does no longer exist, we can interpret lambda as HF times F. So we can use our framework to understand what are the safety margins and where are we in terms of safety margins. We can correlate these design factors and performance factors to design margins. Yeah, to safety margins, I mean, sorry. So you can get into, for option B, for example, in B3112, location class 1, you can actually do an assessment and say, okay, I need at least a K hat of about 0.75, let's say. Yeah, we can clearly see that there is a linear elastic fracture region, an elastic plastic fracture region, and a plastic collapse region. So if you have a K mat of about this value, you will always prevent fracture, and failure mechanism will be plastic collapse. Yeah. 2 minutes. So this is just an example. So let's say you're operating natural gas here, and then you want to repurpose of hydrogen. Hydrogen bitumen makes a point. So you have a strong reduction of toughness. So what you need to do, you need to move to the right just to make sure that you increase your safety margins. So let's say you use an improved NDT, but still doesn't really get you there. So you have to re-rate, right? We can actually develop, based on this, ISO safety margin curves. So we can actually say, okay, I might not be able to gain everything from a better inspection technique, but I might be able to re-rate and get, if I use these curves, I could get the same safety margin as in natural gas. Yeah. So we develop these ISO safety margin curves, so you can use that as a way to test your design. And you can do that for, of course, different, residual stress levels. And there's a range of things I would like to tell you here, but Milos just made me a sign, so I have to speed up. That one thing that I want to mention here is that, of course, the model captures mechanistic things that we already understand. As you increase your toughness or you reduce you increase your normalized toughness, let's say, the effect of residual stresses starts to be more, less severe or negligible. Yeah, a very high toughness material will actually wash out most of the residual stresses. Yeah, so this is actually captured explicitly in the methodology. And the final one, this is one case study. I assess a range of different cases for different materials, and I was interested in understanding the safety margins for different load levels, with and without residual stress levels, which gives you some sort of a confidence on the methodology and how could you apply the methodology for this type of cases. And then I found a paper by these people where they said, okay, this is how, for different flow types and geometries, this is how the pressure versus toughness looks like. And that's quite straightforward to recharacterize or recast into our framework. So we can actually put all these curves into one single framework, which is the UFC, and do a similar analysis, which actually, or make it richer. You can play with the material parameters and the geometry parameters to give more insight. We compare these results, FAD, normal FAD to UFC. We are between, about beyond 0.6 of lambda, which is basically what codes cap in most cases. We are in the same order of magnitude in terms of estimations. And then above that, we are about the 10% regime, which I think is quite acceptable. Finally, so I have just presented an approach, which in this case is used for hydrogen, for repurposing pipelines and storage tanks to hydrogen. The idea is basically to try to link design and assessment, and it can be used to do critical crack size assessment, critical loading, try to qualify any capabilities, and the fact that you don't require the reference stress any longer, and you can include explicitly residual stresses. I think it makes it very, very appealing. There's a lot more of validation to be done. If you come to to my next lecture, you will see how we validated this, but I didn't have the time to do it if I wanted to present case studies for hydrogen. Thank you.